Hello friends, welcome to this video. In this video, we'll be doing this theorem. Before starting this theorem, let me just revise the definition of an isometry. An isometry is a map which preserves the distance. So while proving something as an isometry or not, no need to check is this a linear transformation or not. Okay, so isometry is just a map, not necessarily a linear map. So they have given in this theorem that I have a map from V to V where V is a finite dimensional inner product space over R, and that map satisfies two property, that it preserves the origin and it preserves the distance. That means my f of 0 is equal to 0 and norm of f of x minus f of y is equal to norm of x minus y. So in word the statement become an isometry preserving origin is an orthogonal transformation. So the proof will require two things, that we need to prove it is an orthogonal as well as a transformation. That means it preserves inner product as well as it is a linear transformation also. Okay, so we divide our claim into two parts. We will first prove it preserves inner product, and then we will prove it is linear transformation also, right? So our claim 1 is to prove it preserves the inner product. So my claim 1, f preserve inner product, that is my inner product f of x with f of y is equal to inner product xy for all x comma y inside V. Okay, so they have already given us something. We know that my f of 0 is equal to 0 and my norm of f of x minus f of y is equal to norm of x minus y. This is true for all x comma y inside V. Suppose I use both of this directly, that means I know f of 0 is equal to 0 and this is true for all x comma y. Therefore I know norm of f of x minus f of 0 is equal to norm of x minus 0. Therefore my norm of f of x minus 0 is equal to norm of x, since x minus 0 is x. Well, here also it will become norm of f of x is equal to norm of x. That means from the given two data we can conclude that it preserves norm. Can we conclude if it preserves norm, it preserves inner product? Have we done something similar? Not in this case, because we have done a case in which we have proved it preserves inner product if and only preserve norm. But in that case we have used that f is a linear transformation. But now we don't know it is a linear transformation or not. That is actually our claim. So we cannot directly use, since it preserves inner norm, it preserves inner product. So by using this, but we'll prove it is preserving inner product and the given condition that we have. Okay, so we have this. I hope everyone understood why we cannot directly imply it preserves inner product, since our f is not yet prove it is a linear transformation. After we prove it is a linear transformation, it is done. Okay? But for now we don't know. But we know it preserves inner product, it preserves distance. We will use this too. From this, for any x comma y inside V, what I will do, I will consider norm of f of x minus f of y square, that is same as norm of x minus y square. Okay. So after this, student will prove. I will write one step and other step will be skipped. This minus f of y, right? We know norm square is same as inner product with itself. It is same as x minus y, x minus y. Student will simplify this and they will find it is same as norm of f of x square minus 2 times inner product fx with fy inner product plus norm of f of y square, that is nothing but your left hand side. Right hand side similarly will become norm of x square minus 2 times inner product xy plus norm of y square. Now one more note, since we are working over inner product over R, we can commute this. That means inner product of xy is same as inner product yx. hence only we can write 2 times of this, right? Otherwise the case would be different, but since we are working on real inner product space, we can do so. Okay, so after this we know it preserves inner product. If you want, you can name this as 1. So this is actually same as norm of f of x square, norm of f of x square minus 2 times inner product f of x f of y plus norm of y square. I can write this as norm of y square is same as norm of x square minus 2 times inner product xy plus norm of y square. Cancelling the like terms on both the sides, we get inner product of f of x with f of y is equal to inner product of xy. Okay. One more note. Can I conclude it is an orthogonal now? Yes? We cannot conclude. Since an orthogonal map is nothing but a linear transformation which preserves the inner product. Till now, we have just proved it preserves inner product. It cannot be orthogonal till now. Okay? So, we know it is preserving inner product. We can use this property to prove it is linear. Okay? So, now we come to our second claim. That is, my f is linear. Okay, I hope you guys understood. If for any doubt, just write in the comment box. I will try to simplify this solution also if you want. Okay. So my claim 2, f is linear. So f is linear means what? I want to prove f of alpha x plus y is equal to alpha time f of x plus f of y. Okay. I know something about f of 0 is 0, it preserves distance, it preserves inner product, those are the things that I know. How I will start? I will start, let my ei, I running from 1 to n, be an orthonormal basis of V. Then what you can conclude about this f of ei, I running from 1 to n? Will it be orthonormal? Will it be a basis also? Your answer can be seen from this. We know it preserves inner product. So my ei ej inner product, this is same as f of ei with f of ej, and this is same as delta ij is same as f of ei with f of ej, correct? That means by this set of all fi's is orthonormal, and every orthonormal set is linearly independent. Hence this becomes is also orthonormal basis of V. If student want, they can write in detail that since this is orthonormal, this is also non-orthonormal. Orthonormal sets are linearly independent. Since the dimension of V is n, a linearly independent set of size n is a basis. These are the 3 points that you should write if you want. But I think I can skip for now. Okay. So I know these two are the orthonormal basis. One more question. We have assumed that this set is orthonormal basis. Does there exist orthonormal basis? Answer is yes. For every finite dimensional inner product space, there always exists an orthonormal basis. So we can yes assume that there exists an orthonormal basis. Let it be this ei. Okay. I want to use these two sets to prove my f is linear. So what I will do is, for any x inside V, my x will be nothing but, since this is a basis, x will be linear combination of ei. Let the coefficient be xi, I running from 1 to n. Okay. So if my f is this, what can I conclude about f of x? Can I write this is same as summation xi f of ei? Yes. This is a good question to ask. Okay. The answer for this is no. Right now we cannot write this since we have to prove it is linear. Okay. So I cannot write this directly. Since over here I am using the property that f can be splitted over addition and the scalars can be taken out. I cannot write this directly. But I know why this is also a basis. Correct? So my f of x is an element of V, and my f of ei, I running from 1 to n, is basis of V. Therefore, my f of x can be written as some alpha I time f of ei, and I is running from 1 to n. Okay. Now we are interested in this coefficient alpha I. We know this are orthonormal, so can we write something on place of alpha I? Can we find out this particularly? Okay. So what we do is we consider inner product of f of x with f of ek. Correct? This is some element of the basis f of ek. Okay. So this is same as what? This is same as inner product. This is same as inner product of summation. On the place of f of x, I'll write its value alpha I f of ei. I is running from 1 to n. Inner product with f of ek. Okay. Now I'm not using f is linear, but I know my inner product is linear, hence I can take this summation and alpha I outside. Summation alpha I is running from 1 to n, inner product of f of ei with f of ek. Correct? After this is actually same as delta ij, right? Because we know it is an orthonormal basis. So this is same as summation alpha I delta ik. I is running from 1 to n. This is 1 if and only if I is equal to k, otherwise it is 0. Hence when I is equal to k, it is 1, otherwise it is 0, means implies this is nothing but equal to alpha k. Okay. That means I find out value of alpha k, that is nothing but inner product of f of x with f of ek. Correct? Okay, I need to rub this things. Okay, I'll rub, or otherwise I'll write over here. The next step is my f of x is equal to, from this to f of x is equal to summation f of ei. Okay, I know alpha k is same as this, so alpha I is same as inner product f of x with f of ei. Correct? Inner product I is running from 1 to n. Also we have proved my f is preserving inner product. Mark that equation as star. So this implies this is same as what? Summation inner product. This is same as x ei, right? Inner product of f of x with f of ei is same as inner product x with ei, f of ei. I is running from 1 to n. So we know f of x can be written as this. Now we will use this to prove my f is linear. Okay. So I'll just rub this things. So I will use this 3, but my claim is to show that my f of alpha x plus y is same as alpha time f of x plus f of y for all x comma y inside V and for all alpha inside R. What I'll do, for any x comma y inside V and alpha inside R, I will consider my left hand side, that is f of alpha x plus y. Okay. So I want to use this. How can I use this? I know f of anything can be written in this form. It is same as summation I running from 1 to n, inner product of alpha x plus y with ei, and f of ei is multiplied. Correct? Okay. Now I know my inner product. This inner product which we are using is linear. That means it is summation I running from 1 to n alpha times inner product of x with ei plus inner product of y with ei inside a bracket with f of ei. Okay. So what we do is, now we distribute this f of ei and the summation also and split the summation. We get alpha times summation I running from 1 to n inner product x with ei, f of ei, plus summation I running from 1 to n inner product y with ei, f of ei. Okay. From this 3 only I can write it is alpha time f of x plus f of y. Implies f is linear. Correct? implies me now I can conclude my F is orthogonal transformation. Okay, so now we have proved this is an orthogonal transformation. Hence from now we can conclude any isometry which preserves the origin is definitely an orthogonal transformation. Okay, one more time I will say an isometry may not be a linear transformation. I will give 4 or 5 examples for you guys to solve. You just have to prove is it an isometry or not and check is it preserving origin, and then directly you conclude that it is an orthogonal or not. Okay, so in this process no need to prove it is linear or not, just prove is it preserving distance, is it preserving origin, then it's automatically becoming orthogonal linear transformation, or you can say orthogonal transformation. Okay, so now you see the homework questions.